This is a lesson on the moment of inertia in the rotational kinematics unit. I am doing a lesson on moment of inertia only and by itself because it is a term you will see in several quantities in the rotational kinematics unit. Moment of inertia is the rotational analogy of mass, and what happens is it quantifies how difficult it is to turn an object, or equivalently how much this object resists rotation. It's the rotational idea of inertia. Rather than mass is linear, this is rotational. And so what happens is we need to quantify not only how much mass there is, but how far that mass is away from the pivot point. It depends on the shape of the object, therefore. If there's lots of mass and large radii or small radii, it depends on the dimensions of the object. And the formal definition is using integral calculus, but you will not be required to do that for general physics. The units of moment of inertia is kilograms times meter squared, and you can see this from the general equation I put here. A general moment of inertia is some sort of proportion less than 1, it'll be less than 1, times a mass term times a distance term squared. And it talks about like the radius of the mass away from the pivot point. But for common objects in general physics, you will be given a moment of inertia. One of the most common objects is just a point mass, just hanging out in space, rotating around a pivot point, mr squared. You could have a rod or equivalently a stick. It's called different things in different places. And you can rotate it about its center of mass, or you can rotate it about the end. And you will see a couple of problems that I do that include this. There's hollow or solid cylinders. The hollow cylinder has most of the mass away from the center, so it will have a larger moment of inertia than a solid cylinder that has more mass towards the center if it has the same mass. And same with the solid sphere. A hollow sphere will have a higher moment of inertia than a solid sphere because the mass, equivalent amount of mass, is farther away from the pivot point than if it's solid. And you will be given these in problems if you are required to need them for me. There's a couple of moment of inertia caveats that I wanted to throw in here. And if the first is the principle of superposition strikes again if you have multiple objects rotating at the same rate. You can look at the total moment of inertia, which is just the individual moments of inertia added up. The other caveat here is called the Paralell Axis Theorem. Often when things are rotating, it's not about the center of mass. The previous equations that I showed you were about the center of mass for the cylinders, for the spheres, etc. If it's not about there, if it's at some point other than the center of mass, we need to take into account the Parallel Axis Theorem, which says that the moment of inertia about that alternative pivot point is the moment of inertia about the center of mass plus m times d squared, where d is the distance from the center of mass to the pivot point. And a quick example I'll show you here is, we'll look at this in a bit, a stick where its pivot point isn't at the end and it's not about the center of mass, but maybe we choose some point in between. The center of mass is here, and the distance d will be the distance from the center of mass to the pivot point. So that's the distance d in here. Here's the pivot point, here's the center of mass, that's the distance between them. So for a stick about the center of mass, it's 1/12 ml squared, whatever the length is. And then you would add on md squared, and that would be the new moment of inertia about this point P rather than the center of mass. I've chosen a couple problems of us for calculating the moment of inertia. The first is stacked disks. A smaller disk is placed on a larger disk, which is attached to a frictionless surface and allowed to pivot about its center. So this is a top view. The side view would have one disk on top of another disk, and I can draw it kind of in 3D here. There's the top and the bottom. All right, so one has a smaller radius than the other, and they're pivoting about an axis through their center, and so this is the side view. The mass and radii of the disks are, respectively, 2 kilograms and 0.4 meters and 5 kilograms and 0.7 meters. So there's a smaller one and a larger one. So I'm going to call the top one I1 and the bottom one I2. I1 will follow the general form for the moment of inertia of a disk. A solid disk is a half mr squared. So I'm going to put m1 in here, and I'm going to put r1 in here. I2 is going to follow the same equation, m2 r over times r2 squared. So if I want to find the total moment of inertia for the entire system here, they're rotating together, I would just take I1 and add on I2. So 1/2 m1 r1 squared plus 1/2 m2 r2 squared. And you could factor out a half if you want to when you plug in numbers. I'll do that here real quick. So I get, actually I'm going to leave it out. M1 is 2 kilograms and R1 is 0.4, and I have to square that. 1/2 M2 is 5 kilograms and its radius is 0.7, and I have to square that as well. When you multiply this stuff out, I1 by itself, just by itself, is 0.16, and the units on that is kilograms times meters squared. I did the same for I2. Just by itself, its moment of inertia is 1.225 kilograms times meters squared. And so I'm going to add that down here to find the total. And when I run this through the calculator to find my total moment of inertia, 0.16 plus 1.225, you get 1.385 kilograms times meters squared, and that's the moment of inertia. Okay, so you saw in the other equations, like this is just the moment of inertia. We're going to be using it in other equations that include other quantities, but this is how you calculate a moment of inertia for a system of a couple of objects that are rotating at the same speed. I picked another question here, the putty on a stick. Says a wad of putty, mass m, is thrown at a meter stick, mass big M, sitting on a table. The putty sticks to the meter stick a distance big D from the pivot. Determine the moment of inertia for the two-mass system when, and there's two parts here. A, when the meter stick is nailed to the table at its end, so it could rotate about its end. And then B, the meter stick is nailed to the table at a distance D from the center of mass. Okay, I'm going to note that I wasn't given any numbers, so we're just going to have symbolic values in here. Here's a D here. But that's okay. I can deal with that. I'm going to draw a meter stick. Here is a meter stick. And in the first situation, it's being pivoted about its end. So I'm going to put a big pivot point here, point P. And it says that the putty is thrown at the meter stick a distance D from the pivot point. I don't know where D is, but I'm just going to say here's the putty, come in, and it gets stuck here. Okay, and I'll call this little m for the wad of the putty. And that's where it is. And this here is the distance big D from the pivot point to where the putty gets stuck on that meter stick. I imagine this meter stick and the putty will then pivot in the counterclockwise direction around point P. We want the moment of inertia here. I'm going to note that I have two objects. I have a rod about the end, and I also have this point mass. So I'm going to have to say that I have a total moment of inertia, which is going to be I of the meter stick plus I of the putty. I of the meter stick is an equation you would be given 1/3 ml squared. Just about the end, that's what it is, 1/3 ml squared. And then the putty here, I'm going to note, is a point mass. It's not an extended object. It's not anything rolling or rotating or anything. It's just a point mass. And the moment of inertia for a point mass is m times r squared. And in this situation, the radius from the pivot point to that point mass is the distance d they give us. And so this is a big M, and that's a little m. And that would be our total moment of inertia for this situation, for part A. Part B has a different situation going on. I can have the same meter stick, and instead of being pivoted about the end, it says that the meter stick is nailed to a table at a distance little d from the center of mass. So here's the center of mass. I always mark it with an X. So we're going to let it pivot about this point here. And I will again call this point P. That's the pivot point. And they're telling us that this distance here is little d, from the center of mass to the pivot point. This reminds me of the parallel axis theorem. I'm not rotating about the end. I'm not rotating about the center of mass. It's someplace else on the object. So I'm going to have to remember that I parallel equals I center of mass plus md squared. Okay, so we have d in there. The other thing that I have to put on here is the putty. I'll put it in a different color just so we can see it a little bit better. So there's the putty on here, little m. It came in, got stuck to the meter stick, and it's a distance big D away from that pivot point, right? A distance D from the pivot point. I don't know what this distance is, but we're just calling it a distance D from the pivot point. So when I put this equation together, again, I'm going to have two contributions, one from one object and one from the other object. So I'm going to have I of the meter stick plus I of the putty. I of the meter stick has two terms. We have I about the center of mass plus some md squared because we're not actually pivoting about the center of mass. So this term is going to look like 1/12 big M times L squared. That's I center of mass plus its mass times little d squared. That's the distance between the center of mass to the pivot point. So that's for the meter stick. And then the putty is still a point mass. So it'll have a little m d squared. And that is going to be what the moment of inertia is for the second situation, where you have shifting from the center of mass to a pivot point away from the center of mass. You have to take the parallel axis theorem into account.